Hello everyone, in today's video we are discussing the third classification of voltage divider bias circuit. So here we know that this is a most widely used, so it is a most widely used biasing circuit, and here the voltage divider formed by R1 and R2. So here how our circuit is there, previously we were having the RB connection, so but here we have our circuit has, so in this way, that is RC will flow the current IC, that is resistor collector is flowing the current IC from voltage across the collector to emitter, okay, towards the emitter. So it is having one more emitter resistor which is flowing the current towards the emitter, that is IE. And next here we have, instead of resistor base, we have resistor 1 which is connected to the voltage across the base emitter, and we have resistor R2. So everything is connected to VCC and ground. So throughout this we have only one current, that is IB is flowing, okay. So this R1 and R2 will act as a voltage divider. To understand the voltage divider bias, we'll first convert this circuit to simplify. So we'll use the Thevenin theorem. So we'll use Thevenin theorem. So here we know that complicated network. So complicated network contain multiple resistor and voltage. So containing multiple resistor and voltage source, it convert into single resistor and single voltage source. So how it will convert? It will convert into single resistor, that is RTH, and it will convert into single voltage, that is VTH. So VTH, and which is connected to some resistor load, okay, it is connected to some resistor load. From VTH to resistor it is flowing the current IB. So we have to convert using this method, we have to convert this simplified circuit. So how we'll convert, we'll see. So here we have VTH, that is Thevenin voltage, open circuit voltage across the AB terminal, and RTH, resistance from terminal AB when all voltage sources are short circuit. So by using Thevenin theorem we will convert our circuit. So we'll keep VCC, resistor RC which flows the current IC across the terminal VCE, voltage across the collector and emitter. So this resistor emitter is also kept constant. So we are converting our circuit, that is we are converting this circuit into R1, R2 which is this part we are taking as load part, which is connected to VTH. So this part, this is converted as load, so it is taken as load. Okay, so we have formula that by using KVL, so from BCC we'll check for current flowing across IB. So from BCC, register which flows current across IB. So by using KVL from BCC we are checking from BCC to IB. So we get VCC equals to IB into R1. So from VCC, what all the register it is taking? IB into R1 plus IB into R2. Here we can take IB as common, R1 plus R2 VCC. So when we send VCC R1 plus R2 here, so we get our IB value. So we can say this as equation A, and we can find our VTH value now. What is VTH? VTH into IB into R2. How this we are getting? So this VTH we are getting current across the base emitter. So VTH equals to IB into R2. So what is our IB value? So put equation A in VTH. So VTH equals to VCC into R1 plus R2 into R2. So this is our VTH value. And what is our RTH value? So RTH is a combination of R1 into R2 whole divided by total number of register R1 plus R2. And we have here our constant values that. So now we have got the value RTH, VTH. Now we'll search for input section circuit. So what is our input section? So let us take input section. So we'll take from VTH to VBE. So we'll the input section VTH to VBE. So what all it consists of? So it will consist of R1, R2, even it will consist VBE, means this part is also VBE. So it will also consist I into RE. So our by using KVL we get VTH minus IB into, instead of R1, R2 what I am writing? I am writing as RTH minus IE into RE minus VBE. So even this register emitter and current will flow across the voltage base emitter. So we'll get this. So this as a value, and we have a condition that, so we have one condition that here whenever the current is flowing from emitter, so it flows, so here we can say IE equals to IB plus IC, and we know IC value has beta into IB, so we can take IB as common, beta plus 1. So we can replace this IE value. Yes, we can replace, right? So we'll replace as VTH minus IB into RTH minus, instead of IE I am writing beta plus 1 into IB into RE minus VBE equals to 0. So now I can take the IB value as common. So I will take IB value as common. So VTH minus IB has a common. So I will get RTH plus beta plus 1 into resistor across the correct emitter minus VBE equals to 0. So our total current which we will get as VTH minus VBE whole divided by RTH plus beta plus 1 into RE. Now we can replace this IB value into IC, right? What is our IC value? So our IC value is beta into IB. So what is our beta? IB value what we have? So we have got VTH minus VBE. So IB value is VTH minus VBE whole divided by RTH plus beta plus 1 into resistor of emitter. So this is our IC value. Now we'll see the output section. So our output section, so here we can see our output section. So it is from VCC to VCE. Here we have not converted anything VTH. So we will check directly from VCC to VCE. So our output section is from VCC to VCE. So using KVL we get VCC minus current across the collector through resistor and voltage across the emitter minus, so current across the emitter. Here we have one condition that IE is equivalent to IC. So here we have condition IE is equivalent to IC. So VCC minus IC into RC plus resistor emitter minus voltage across the current equals to 0. And VCE equals to VCC minus IC into RC plus IC into RE. So this is our final equation. So we'll solve problems in next video.